Well, we have defined our is arithmetic surfaces on the blackboard the definition. We just stick to the notations introduced. I remind orally that both the base and the fibers are supposed to be one-dimensional or better dedicated schemes, and we are going to consider parallelly the geometric and the arithmetic versions of it. So today we turn to the most natural questions concerning any concept, any mathematical concept. That is the question of constructing arithmetic surface. The definition has been given, so it is natural to try to think about all of them, all the arithmetic surfaces. Now, the geometric version turns out to be easier. I'll explain why. Let's use our notations over the ground field that is assumed to be algebraically closed. When I say easier, please don't take it literally. The question of considering all the arithmetic surfaces, or in this case, all the families of curves, is a very difficult mathematical question. However, the definitions are relatively clear, and we'll discuss them today, maybe concentrating especially on the case of genus 1 families. So, as for the arithmetic version, the equivalence is not so clearly defined. I mean, working in algebraic geometry, we have a very clear concept of isomorphism of the objects, or rather maybe two concepts of biregular isomorphism and birational isomorphism. As for the arithmetic case, the question is much more delicate, because considering two arithmetic surfaces the same or equivalent, we should always keep in mind the question concerning the possible isomorphism between them. That is, we should check check over what the isomorphism is defined. I'll say it now in the most naive way. So somehow, if we are discussing the equivalence of two sets of solutions of the solution can be transformed somehow, one into another, one set into another. But the transformations themselves can be defined over different fields and rates. Therefore, it is a more delicate question, and today we must concentrate mostly on the construction of arithmetic surfaces over in the geometric setting over here. So I would say that there is basically two geometric ways. I put aside just writing down the equation. It is obvious, but we are going to discuss the geometry. So there are basically two geometric ways. One is very easy. The other may need the whole lecture, but I'll ask you whether you are aware of the concepts. So there are two ways. The first one can be easily drawn. Let's say this is a surface. To switch on your geometric imagination, you can even assume that it is embedded in P3. Then you take the line and consider the family of the surfaces. Not sure it is very clearly drawn. Let me see. Something like that will look better perhaps. I'm trying to draw the two planes of the family. So I somehow, how do we parameterize it? So let it be a line A, and let then be pi, say sub alpha, in x. Oh no, the index is going to be b, I, b, I, b here, and x. X, that is the total space of the family. In this case, it's just the arithmetic surface, and x sub b is pi sub b intersected with s. Here b is parameterized by the projective line. I hope all of you understand that the set of plane in the projective planes in the projective 3 space is parameterized precisely by the projective line. It's one of the definition, or you can take the transversal to L, and parameterize the planes by their intersection with this transversal. So then what we have is X. I'll write down the broken arrow. So the base is B bold base, and the line is, the arrow is of course broken because for two reasons. The first reason is that this projection is obviously not defined on the line itself. And I have to ask the question. Please raise your hand, those who is going to understand what I'm going to say now. In order to complete this arrow, we need to blow up this line. Almost everyone. Good. Anyhow, in our theory is basically birational, and so this projection is geometrically defined. The other reason why it is defined, not everywhere, is that some we have supposed that S was smooth, and then according to the classical theorems of algebraic geometry, the general intersection of a smooth surface with a plane is also a smooth curve, but almost always there are some singular fibers. Some planes are not transversal to the surface, and therefore the corresponding intersections are singular. Then we throw them away. So this is the first method. I hope we are going to discuss it in the detail in the simplest possible case, and you can just tune your imagination for considering this case. For example, the surface can be a cubic surface, and then choosing any line. Perhaps we should be careful not to choose this line as one of the 27 lines lying on the surface completely. Sorry, I'm afraid that I didn't stress that the line, the line here of course does not belong to the surface. And then we have a family of cubic surfaces, and it is a very fundamental object. It is simplest case, is a very fundamental case in arithmetic geometry. It is the simplest one that is not trivial, because if we consider surfaces just quadrats, surfaces of degree 2, this construction will give something, I would say, not very interesting. It also deserves some analysis. But perhaps we are not going to pay attention complete. And this one is as big as possible, and both its fibers and the whole families have a very interesting geometry and arithmetic. As for the geometry, it is completely understood in 19th century. As for the arithmetic of both cubic surfaces and cubic curves, it has lots of open questions, and we'll formulate some of them. So this is the first way. So I was speaking about a very particular case. Of course, there are lots of versions, and the surfaces can be of larger degree, or they can lie in the projective spaces of larger dimensions. However, the picture is clear and interesting, even so it's clear in all the cases, but is interesting even in this seemingly simple case. Any questions about this way of constructing surfaces?
A question about that projection from X to that.
Yes, I'm afraid I did not define it properly. The projection is defined in the following way. Take a point here. I'm trying to define it geometrically. It is rather easy. It's difficult to draw. So take an arbitrary point on the surface and consider a plane through this point and the distinguishing line. Then it will distinguish a certain plane from this family. This plane is associated with a chosen point. Sorry for not saying it.
And then how does the blow up work here?
Sorry?
How does the blow up work here? You said you want to blow up you want to blow up.
What is to blow up? Oh, we just blow up this line in between three. Then the pi becomes defined in the blowing up.
Okay.
In which sense did we define a surface? So I see the definition as an equation, but what are the new things that we know about?
The new?
Yeah, about the surface after that.
Compared to the surface itself as an object of algebraic geometry, I mean?
Yes.
Well, it is stratified, it is fibered over the base by the curves. It was just an abstract surface, but we consider its morphism to the projective line, the fibers of which are the sections of the surface by hyperplanes.
Okay, got it.
This is the additional structure. Thank you for the question, because perhaps it is a good point to recall the purely algebraic picture of it. So we have the field of rational function plus, well, better I use x, x, a of x, the transcendence over k here is 2, then we have a base such it is related to your question, abstractly, we are working with an arbitrary model of the field, of a field, of transcendence degree 2. Yes? And now, when we include such a thing, we have an intermediate object. Its place is somewhere here. Intermediate object of transcendence degree A1. So, algebraically, it means the choice of the intermediate field in the extension of fields of transcendence degree 2. Geometrically, it means what we have drawn here. More questions about it? Good. Then we turn to the second way. I'm afraid I have to erase this one. And the second is consider all the curves of a given genus G. Here we mean perhaps everyone understands me that this means that given by G is dimension of X sub B only. So, this definition of genus works also over in the case of singular.
It's first. It is a first homology.
Yes, sorry. And this definition works also in the case of singular vipers, and it is the definition of genus in that case. Now I'd like to have an idea of what about this set of all curves. Assume here that J is strictly positive. And please you raise your hands, those who has an idea of the moduli space of curves of a given genus. Such heads. Okay. Then, since such is 1 out of 5, I will not assume this concept as known, and lots of things have to be said about it. So, by definition, the moduli spaces of the K is the set of curves of genus J over the isomorphism. The isomorphism can be defined and understood in several ways. And the easiest one is to consider the objects we are discussing, again, in the same purely algebraic way as we were using before. Then the curve, is defined completely by the field of rational functions on it, which abstractly is just a finitely generated extension of the ground field of transcendence degree 1. And the isomorphism is as easy, as natural as possible. However, the dimension 1 of the curves is an easy dimension when every field of rational functions of the class I have just mentioned has the unique canonically defined complete smooth model. So you can think about the set in the numerators as about the set of complete smooth curves of genus J. So it is very well defined, though the story was quite dramatic. It was written down, Riemann in 918, I don't remember exactly. So defined it over C, but heuristically. And then like Müller alphas, yes. Oh, sorry, I will include something. Alphas, yes. In the middle of 20th century, like this, developed a transcendental theory, quite rigorously. Well, in between the Italians, various Italian mathematicians, from whom we maybe should mark especially Francesco Severi. So on the wedge path, so 19th and 18th century, used algebraic, worked with the algebraic definition, but also heuristically. And it was only in the second half of 20th century when Gubkina Mumford in quite a remarkable paper that is still very hard to read. So it is was 1960 something. 60 something, that was both algebra, geometric, and rigorous. So for about half a century, we can use this set. Sorry, as a set, it is of course defined without any efforts of remarkable mathematicians, but it turned out to be the quasi-projective. Manifold of the dimension. Maybe I'll use sometimes such a special notation, 3J over 3 underlined, that is true 3J minus 3 when J is larger than 1 and just 1 when J is 1. And this is the dimension of the moduli space, or the number of parameters from of which the general curve of genus J depends. The precise definitions of these moduli spaces can occupy the whole semester, and I tried it several times. It is really hard and I think very interesting mathematics. However, with low genera, we can describe it quite explicitly, and today, after some generalities we are going to discuss now, we'll remind ourselves the genus 1 situation. So, now I'm in a difficult position, as everybody speaking about this thing, so I use the non-standard approach to it, and we'll say about the dream of universal family. What would it be? Well, maybe I caution you just now. The object of this dream does not exist in any genus. It is close to exist, but does not exist actually. So, if it would exist, look what it would be. Here is the modular space. Here we have a class of some curve x, and we'd like to see this curve together with the projection. Well, I think we did not assume that the global dimension of our families is always 2. Here it would be arbitrary, so it would be a nice object where all the curves of a fixed genus is collected together with the projection to the moduli space that associates a class, isomorphic class of every spaces as they are. Good. Let's give a name to this non-existent object. I'm not discussing crazy things just because, as I said, some objects there are that are quite close to this universal family do exist. There are just certain variations of it. So I have to emphasize that formally we are under the wrong assumption. If U sub J, let's linear over Mj existed, for each arithmetic surface as we consider it, x over b, sorry it's a bad letter, let's denote it u small, the projection of the universal letter, and we'll stick to our bias for the variable family of curves. Then there would be a characteristic mapping denoted, say, comma x. X was written differently in bold font. Kappa x to m sub j. It is a characteristic family, and by definition, kappa sub x. Sorry, there is a small notational detail. As everybody, we denote by x both the triple of x by b and the space x. Otherwise, there are too many letters to write. So, kappa sub x maps, so b to the modified space, setting every b bold space here, usual b here, to the isomorphic class of the fiber over 8x sub b. And sorry, this construction does not depend on the universal family, and it always exists and is well defined. But if now we add this fantastic part, u sub j, universal family, you perhaps better also use the index here, small u sub j here, and then if it all happened, we could say this is a very natural, so I write it here, and then in this fantastic case, x would be just defined as a fiber product. X could be defined as the fiber product of B over universal space, with universal space over the moduli space. So in this case, all the families of over B, here we fix the base over B would be in the canonical bijection with the set of morphisms in the appropriate category. We usually mean that in the geometric part of our course, we usually assume that we work with the projected varieties, so the morphism is understood exactly in this way. So would be the set of morphism on B to MG. So there could be a nice question like this, a nice description like this, and a nice way of understanding all the families. We have a hint here, according to which describing families, we better first fix bases and then consider all the families over those bases. And in our construction one, our bases were just projective line, and it is a very nice set of objects. Here, in this case, we would have just the set of rational curves inside moduli spaces, or mappings of, yes, it is exactly so. We would have the parameterized rational curves over MG. Now, to work with, to discuss this construction in more detail, as I said, it is nothing but a dream, but there are basically two ways of curving it. First, let us reformulate what has been said now and consider the functor. Of families. Sorry, I'm afraid we did not introduce the notations for our categories of algebra geometry. Objects, let's do it now in the obvious way. So we consider the category of varieties over a fixed algebraically closed field K to the category of sets, understanding the the argument of this functor, sorry, we have agreed to use to duplicate the set theory notations. So here we are considering varieties as basis of the families. So we have a notation for it. So send it to the set of families. X over B up to the equivalence, where the equivalence is defined in an obvious way. If we have one family and another one, then the families are isomorphic over a base if there exists such an isomorphism with this diagram being commutative. So, since
Is there an X on the left side?
on the left side of
You roll the B maps to
B here, are you looking here?
yeah.
It associates to every base the set of isomorphic classes of families over this base.
Okay.
So it is correct.
So B is not a project line.
No, it is an arbitrary base. Arbitrary
Well,
base.
assumed. That's
So since it is just a dream, since such a thing it means in the categoric language, it just means that the functor of families is non-representable. If it were representable, we could define the moduli space in a very short way as just the objects representing the functor of families. But we have to do certain tricks to return, to get the representable functors. Any questions about what is written now on the blackboard? If some of you are not in very good terms with the categoric language, then please believe that this is a concise way of saying things. For the time being, it is just the claim of some non-existence, but perhaps I have a general categorical comment about that. And I'd like to draw a parallel between what we are discussing now and what we have discussed in the very beginning of the lectures concerning the functor of points. At that time we have got lots of representable functors, and basically we understood that solving equations, algebraic equations, is just applying representable functors. And I don't know any understanding of that, but I would say that for me it would be a rather difficult task to give an example of a functor that satisfies some natural axioms of algebra geometric functors, but is non-representable. And here is the very basic example of that. Now perhaps we turn to some down-to-earth mathematics just to see how this, first we have to understand why it is not representable, and we will do it immediately, and then we will discuss how to overcome this difficulty. So, I'm afraid I have to erase almost everything. The idea of constructing all the families of curves with given base by the universal construction, I hope, is clear. So if there are no questions, I erase almost everything and explain the non-representability of the family of functors. And perhaps you feel, as I do, that there is just a minor irritating obstacle to this representability. However, non-representable. Let's explain this. So consider the family X. Defined by the equation like this. Minus epsilon. So we supplied by the structure of the family just in this obvious way. Perhaps I better write it this way. Epsilon and epsilon inverse formally would mean that we have an epsilon line here with the zero punctured, and over every epsilon we have a curve defined by these equations. By the way, we have considered the families, a family like this, when we have discussed the congruence and all our elliptic curves in that problem were isomorphic over the algebraic closed field over which we were perhaps the Q bar. But they are not isomorphic arithmetically. That's why the problem of congruent numbers is a rich mathematical problem. So fact is that this family is isotrivial, and I'll explain in a while what does it mean. The family is trivial if it is just the direct product of the base and all the fibers. Here the fibers are isomorphic, but the family is not trivial. Perhaps let's explain it now. Non-triviality. Over C. I'm not saying that it is completely obvious, but I'm sure it's a good exercise or a good question to think about. It means that when our base, the epsilon plane, is the complex plane, and away from zero we have the complex torium, then going around the puncture has a non-trivial monogamy, one of the main geometric constructions related to the families of curves. It means that whenever we take a cycle here on some fiber, take a cycle, maybe I better draw this one, and you can check. The best way is to use uniformization, that is, consider these curves as the factors of a complex line, or complex plane, I don't know how to call it better, by the same lattice, the square lattice. So when you go around the puncture, this cycle will transform into something non-trivial. The best understanding is the accurate drawing of it, preceding the formal understanding.
The formal understanding is this monodromy acts on the first cohomology.
Or cohomology or homology. It is geometrically clearer to consider the homology just in this way. When you go around it, the homology changes its basis. It deserves some drawing, imagination, and so on. Perhaps there exists some shorter and more formal argument. I'm used to this one. So, as it is obvious that the trivial family has the trivial monodromies, the family is non-trivial. However, since the fibers are isomorphic, then our epsilon line is mapped to a certain point. So here is the kappa, the corresponding kappa, it would, so epsilon line is too long to write this, but well. Since the image of this characteristic mapping that really always exists and exists in this case, though we have not yet defined or described M sub 1, perhaps we have to write it, to draw everything again, U sub 1 and U small sub 1, and then the spectrum of K, just the punctured one, K epsilon inverse, so fiber product with U sub 1 over M sub 1 with these pairs of morphisms would be trivial. Would be trivial. The fiber of it would be a pullback of the unique fiber of this family. So this is the reason because of which the universal family does not exist and the functor families is not representable. But we see that it is just a minor reason related to certain additional isomorphism. Oh, sorry, I have not explained why not explained the usual meaning of the word isotrivial. It just means that it becomes isotrivial after some base change. And I have to explain it now. So here is the family. Now consider the base change. That's right. Informally include the cubic root of epsilon. It is epsilon is just a variable, not a number. I hope you understand that. And including that means that we consider here the same thing, K of epsilon inverse. I have to write spectrum. And here consider the square root, that is epsilon being an eta cube. And then the corresponding, sorry, it is better to draw it here, K of spectrum of eta inverse in such a way that epsilon is eta cubed. Then we would have here in the will have the equation y squared, that is x cubed minus eta cube, and it is isomorphic to say y squared to the y squared, that is x cube minus 1 under the transformations x being x over eta. Or to define, I believe it has to be a sixth root. And here a sixth root. And then x would be like this. I have not enough space, so y squared is x cubed minus eta to the 6. Now we divide it by eta to the x and see that here we have y over eta cubed squared is x over eta squared cubed minus 1. And then we introduce the new variables, x being x over eta squared and y being y over eta cubed. So after the simple base change, just associating the sixth root of 1, we get the family that can look the same, but this algebra geometric family is really trivial. That's why the original one is isotrivial. Any questions about this family?
Well, so the trouble was that we have, topologically we have a bundle over a punctured plane, but this bundle is not trivial.
Yes, it is not.
Okay.
Again, it is isotrivial. It is isotrivial. It becomes trivial after the base change.
Okay. And here base change is the same thing as, well, to take a
Cyclic covering of the sixth order cyclic covering of the base of the function. Other questions? Perhaps those who know something about algebraic curves will understand that for larger J, there is something similarly. For example, we can consider the hyperelliptic curve like what was this x? One minus epsilon. It would be exactly. It would behave exactly in the same way. It's just a bit harder to follow the non-triviality of the monotony. So what we have discussed is by no means special for genus 1. Just deserve an attentive thinking in the case of genus 1. Now, to understand what to do next, I have to know what is the participants' knowledge of elliptic curves of the curves of genus 1. No questions about these matters? Okay, I erase everything. There are two ways of understanding the question about elliptic curves. It could be the knowledge of cubic curves or really elliptic curves. So please raise your hands, those who knows what is the Weierstrass canonical form of the cubic curve. About 3 hands, yes? So, then what should I really do? Well, very briefly, I tell you the whole story about cubic curves, and maybe there will be something new for those who didn't think about cubic curves over the arbitrary field. So, in the homogeneous form, the equation would be the sum of C, I, G, K, C, X, I, Y, J, C, to K, or I plus G plus K being 3. In pi 2 with the only restriction that say C003. So these coefficients are defined up to the common equivalence, and the last one has like this. There are 10 of them. So let me write it in a bit more accurately. It is supposed that the tuple of these coordinates of these 10 coordinates is not completely 0, does not consist of zeros, and then they are defined up to the common proportionality. So this is a point of pi 9. There are 10 such coefficients. Now, in case where there exists an inflection point, we choose such coordinates that it is given by the equation z being 0, and this line is considered as the so-called infinite line on the projective plane. And then we turn to from the projective coordinates to the affine coordinates. I'm writing them down in the shorter form. You can well, in a shorter form, it is just replaced by x over z, y, b, y over z. And then you check that the general equation under some mild assumptions turns out to be like that. I am choosing some signs, and then it will be a y squared plus b x y. No. The coefficients are bad enough, so I prefer to see it explicitly, but I'll try to guess. So y is minus, y squared is minus c, it was minus 21 y squared plus c, I guess, minus c111 x y minus c, so I have y here, that is, it was 0, 11. Well, it is not so important, but I prefer us to see this equation as exactly the same as that one, y, and then it is x cubed here, and this is c3 plus x squared here, it is c201 plus c plus x here, and this is c102, and finally c003. I hope I was not mistaken. I've checked it many times, but with the whole details, and it takes some time. Now, we see that this one we can consider C all 21 non-zero. Otherwise, y is only in the first degree, and would be like this. And in the same way, C300 is also non-zero. Otherwise, the whole degree would be 2. Therefore, up to the scale transformations of x and 1, we can consider this one as 1, this one also as 1, and have the equation in some form: ax y plus b y. There should be 5 coefficients. And for some time we have to stop here, and call it the Tate form of cubic curve. And characteristics, we cannot simplify this form in a universal way. More than that, we are used that there in the traditional equations of elliptic curves there are no cross term like xy, but we can kill it only over the field of characteristic different from 0. So, in general, we have in arithmetic geometry, we have to work with this case. However, as soon as the characteristic is different from 2 and 3, by further transformations like y minus half sorry. Ax I believe, and then xa to x minus c over 3 and something in between. As you see, we actually use the assumption that characteristic is different from 2 and 3. And then we get to the standard form. Perhaps we call it the Weierstrass form, though there are several ways of understanding it, of understanding what a Weierstrass form is. Minus ax plus b. And then our moduli problem, or the problem of universal family, arises again, and we ask ourselves, is it possible to make this family depend on only one variable, well, only one parameter? Or in other ways, let's see how can we transform it. So we have a, b, parameter than x, y, would be transformed by, say, for the whole thing to be again multiplied by lambda cube. AB is the last to be written. Well, B is so x is multiplied by lambda square x and y to lambda cubed x, then b to lambda to the 6b, and a x to lambda, I guess so. Where lambda is a multiplicative parameter, or in other words, k, it is almost moduli space. That's denoted in some A, B punctured, because there is exactly one point on the infinity of this curve, and what we have defined 1 as the final result of factorization. A, B over this action over the multiplicative action. Well, however, such a factor does not exist. So it can happen that that there is a very nice algebraic family. Here it is the AB plane. Maybe we mark that our set of AB is isomorphic to this family without a semi-cubic parabola that is related to the singular cubic, and the multiplicative group acts in an obvious way on the AB plane just by, was it correct? No, it is not. For this is correct, and AX should be like this, perhaps. Then no, this is also correct. I'm not sure about A and B.
Maybe lambda.
False. Yeah, here we have a fourth pole, so that we acquire lambda to the sixth. So we have the action, a very nice action on the of the multiplicative group on the plane, either on the whole plane or on the complement to the semi-cubic parabola. But the vector over this action, well, does not exist in the category of algebraic curves. Well, if it existed, it would be, of course, a curve. And, well, I think I stop here because there are some important formulas. And, well, I wanted to make this lecture a bit shorter, since I don't feel well. But we need lots of formulas here that are quite important, and I don't know whether I better write them in the ready form or we calculate it. Perhaps once again raise your hands who knows what is G invariant, together with all its multiplications by 12 cubes and so on. Yes, you know. Well, then, I don't know. No, perhaps completed. And now, then, I've made all the calculations before. So, the J invariant in this. However, there is the invariant of this action. And the non-singularity is just the condition that for a cube plus 27 b squared is non-zero. Here's the equation of this semi-cubic parabola. And then the main G invariant, by definition, is what is, well, a straight range multiple here, 6, 9, 12. The obvious part of it is that we want to put the non-singularity condition into the denominator in such a way that it would be defined at any non-singular curve. As for 6, 9, 12, it is 2 to the 8th, 3 cubed, 3 cubed. And the question occurs, maybe we can write down the family with J invariants. And the answer is yes, we can. Perhaps I raise something here. And write down the Mumford family. Easy to memorize. It is the family of the form x plus 1. Then you calculate its J invariant and find out that it is the family with y being cos x cubed minus the factor that is not so easy, not so difficult to memorize. And then we have G here and G minus 12 cube. There is a holy number in the whole theory of elliptic curves. So this is the Mumford family. And M1 is very close to be just a J line. And over every point besides 0 and 12 cubed, we have quite an appropriate, we have a universal family. However, it breaks at J when J is 0 and when J is 12 cubed. The formula does not work. And it is a typical situation. Perhaps we call it the almost. It is an almost universal. In some sense, we can also say that therefore the families of elliptic curves are the functor of genus 1. The family functor of genus 1 is close to be representable. I mean, take any family, throw away the fibers with invariants, with two special invariants. I'll remind in the beginning of the next lecture what they mean and why they are so remarkable. And then you get any family induced from this universal one. So this is one of the almost remedies in genus 1. In fact, there are no such trick in higher genera. However, it gives some idea. So just to conclude and to recall our picture with inducing formula, that for any function, rational function, on any curve, as soon as we consider the values of this function that lies in the G line, we induce some family of elliptic curves. And this is the second way of understanding all the curves with elliptic fibers. However, the equivalence, using such understanding, the equivalence between the families should be different. Basically, we need a type topology to do that, but I'll explain the same thing in an elementary language. Okay, then, any questions concerning today's lecture?
So I have a question about isotropicity. So is Mumford's family somehow not trivial?
Oh no, they are not. Of course they have. Over J we have a curve with, sorry for tautologynous, it is a curve of J invariant J.
So
It's just a good for a small exercise. Calculate J invariant of this family. The answer is, it is J. This curve, the answer, it is J.
and is it clear that we cannot extend the base here? So well, this is not trivial, right?
Yes.
And how do we check that? Can we check?
Well, here I use the understanding that the J invariant is really a true invariant, and two electric curves are isomorphic if and only if their J invariants are equal. And here, over all the base J, we have a curve with its own J.
So you mean that functor families with that certain property that G invariant does not attain two values 0 and 12 cubed. So this functor families is representing.
It's not.
Representing. It's not
It would be representable if this family included all the curves, but it includes all the curves but two of them.
Well, but if we restrict our class of families by the families that do not have these curves.
Unfortunately, in dimension 1, it's impossible because the image in the M sub 1, the image of any base under non-constant family is isomorphic. We can throw away the special curves from the original basis. And as I said, it is one of the ranges.
Okay.
But it is definitely not a functorial way to solve the problem. In the next lecture, I'll show you how to solve it functorially. But we'll have to give extra data to curves. Other questions? Good, then thank you for your attention and see you in a week.
Вопрос. Можете сказать, вы можете платить на сумму?
Да. То есть одному человеку из Парижа я послал, он подключался. Я не знаю, как сегодня.
Куда вас можно попросить? Куда вы можете попросить?
знаете, нас проще всего просить мне письмо об этом. Ведь чистого эксперимента, может, я бы немножко предпочел, чтобы вы где-то зарегистрировались и официально спросили, вам его дадут.
Я просто не понял, у кого спрашивать, я-то зарегистрировался. Нет.
А кто вам писал письмо о регистрации?
Никто не писал.
Никто не писал. Ну, найдете адрес Горчинского? В общем, занимается этим Горчинский.
Ага. А вам, если что, куда нужно писать?
У вас нет моего.
Да.